Perfect. And I can switch off my video just to save the bandwidth. And one more minute, and then we can start. Well, so let's start then. So today we will be discussing the most important section of this course, that is the hardware part. So we discussed the fundamentals of quantum mechanics. Then we discussed about the quantum gates and quantum circuits and qubits. The second part. In the third part, we discuss about the quantum algorithms. I mean, so we discuss only one algorithm. And today then we will going to discuss the hardware. So, so
Sir, before starting, I have a question of the previous day, on the topic of previous day.
yes.
Would you please repeat shortly, in a brief way, the kickback phase that we were doing? That is a minus sign before the expression, and the plus state is going to minus state. Actually, that there is some confusion.
Uh, Say again, which state? Can,
The kickback phase, actually,
uh-huh.
uh, there was a minus sign before, and the zero plus the upstate and
Okay, okay,
downstate.
okay. Okay, I understood. I mean, so when I said the oracle
Yes,
is going to act on this 2-qubit state,
yes,
and this is going to be equal to -1
yes.
fx, and this whole state will going to be there as such. Yeah. So what is the question?
There is whether this -1, whenever the powers are odd, then the minus sign comes. That
Yeah.
is whether that is called the kickback space space phase, kickback phase, actually.
Yes, that's correct.
Okay, okay, my confusion is clear.
Yeah.
Clear, okay.
Okay. So coming to our this section where I was telling that we're going to discuss the quantum computing hardware. In fact, hardwares, there are many platforms. So, I mean, already in my initial lectures, I told you that there can be different types of platforms. So out of them, one is the superconducting, qubits. Of course, other platforms also available. For example, ion trap qubits. I think in our class here, we will be able to discuss only these two in details. And in ion traps, again, there are two categories. So one, we will discuss about the fault trap based. Just a minute. Yeah, okay. So other will be on the panning trap. And in fact, in the superconducting also, we're going to have a different categories. I will discuss one by one today. Of course, after that, we will also going to have a photonics based. But as I mentioned that we will not be having too much time to discuss each and every platform. So what I planning to discuss only these two categories. So one is the superconducting qubits, other is the ion trap qubits. So first of all, I will focus on this part, superconducting qubits. So in the superconducting qubits, there are three fundamental variables which can be used to create logical qubits. And those fundamentals variables are charge, okay? And accordingly, we called those qubits as a charge qubits. Then in the superconducting, we can also use the flux as a variable to create qubits. And accordingly, we call these qubits as the flux qubit. We can use the phase, superconducting phase of the Cooper pairs as a variable to create qubits. And accordingly, we give those qubits or name them as the phase qubits. So based upon these three fundamental variables, one is charge, other is a flux, other is a phase, we can construct different types of qubits. No? So for example, the earliest, or I can say the first qubit which was realized in the superconductors are known as the charged or charged qubits. And sometime we called Cooper pair box or CPB. So this is what I will be discussing today in detail. But I'm just giving you some overview how many different types of qubits exist, okay, in the superconducting category. Then second, and here I think I also must write, if you talk about quantum variables, means the variable used for the creating qubits are nothing but a number of excess Cooper pair. You know, Cooper pairs are nothing but a bound state of two electrons with the opposite spin. So in the charge qubit, I will tell you what I mean by excess of Cooper pair. So if the Cooper pair, normally you have large number of Cooper pairs, and that is the normal situation. And then you add one more, that is called excess. Okay. So that additional, we will see that if you have we're going to call the bit like n equal to 0 or 0 bit. And this is means 0 excess of Cooper pair. And if let us say n equal to 1, then we will going to call as the 1 excess, 0 excess Cooper pair and 1 excess Cooper pair. So if you add one extra, okay, then that state is going to call as the 1. And then we'll see, we'll try to see today that how we can create superpositions and how to create different types of gates in this situation. Then there was problems in the charge qubits, and looking at the issues of the charge qubits, which I will discuss today, and the issue is the charge noise. So this device, based upon the charge qubits, they are very sensitive to any extra Cooper pairs. So that limitation has been removed up to certain extent by another variant of a charge qubit that is called a transmon qubit. So in principle, I can say this is the improved charge qubit. So it is an improved version of the charge qubit. Then quickly I can discuss, and then I think we can come back to our major part. Then, of course, as I mentioned, that we have a flux qubit. And of course, in this case, the variable, when you talk about a quantum variable, this is going to be a magnetic flux. Then fourth category is called phase qubit. And here the variable is phase. So you can change the phase is, see, in the superconducting material, the magnetic flux is also quantized. The phase is also variable, okay? So you can use them to create a qubits. Similarly, there's a further category. So this transmon is further improved, okay? So charge qubit improved to transmon. Trans4 has a further improvement that is called the xmon qubit. If I say in the laboratory, so in the laboratory, people actually are using this one and this one. There
So what
are two.
is this transmon? Is a device, is a semiconductor device or what? So what is transmon stands for?
I'm just coming. Okay, just wait. I'm just giving some overview, and I will explain each and every part in detail. So
Okay.
X1 qubit is the, again, as I mentioned, that it is the now uh, extension of the transmons, and another is the fluxonium. And this is actually, I can say, having a combined feature of flux and transmon. So, but this is still, I think, in the lab frame. I mean, in the laboratory only. It has been not yet has been realized. So another is the gatemon. So these are the possible categories. Okay. So this is also in the lab. Still, research is going on on the fluxmonium and the gatemon. So as you mentioned that key transmon, no? Now I can give one or two lines on each. So when I say transmons, as you can see, these names has been uh, no, came from the active components which has been used to form the qubits. So when I will discuss the transmon, so you will see that key in the transmons we are using the transmission line. transmission line and plus qubits, or we can call as the mono stable qubit. Okay, and now you can see that why this is called as the transmonium or transmon qubit, correct? So, but when I will come to the structure, then you will now feel better that why uh, how these transmission lines are used here. Okay, and phase qubit, flux qubit, already name suggests flux has been used here, phase has been used here. Okay, when you come in the X-mon qubit, so X-mon qubit is again kind of a transmon qubit only. It is a transmon qubits, but with a special X-shaped wiring. So the wiring here are very unique. So maybe if we get time, then we will try to see, okay, what mean by this now X shape. Okay, what is the mean by the X shape wiring? Okay, but because of this X shape wiring, this is what is got the name as a X-mon. Okay, it is a of course a transmon qubit. So mon is still there. Okay, but because of X, it got the name X-mon qubit. So fluxomion means again it is using a flux, is advanced version of the flux qubit. And but as I mentioned that this is still in the lab, and people are still trying to do some find some way to bring on the on the industrial level. The last one, the gate mon. Okay, so this one, you mentioned that the uh, what I can say, this is again, it is again transmon type of qubits. Okay, but here generally people use some semiconductor switch. So these are the nothing but a transmon qubit with semiconductor gate. And here this qubit frequency, okay, in this case in the gate mon, one can tune, okay, by applying the voltage. So so there is a, I mean in this case, because semiconductor there is actually a called gate electrode. So one gate electrode is being used, okay, and this gate electrode, so it is something like, if you look at the structure, if we will get some time to study about this. So this is actually a semiconductor, sorry, superconductor, then semiconductor and superconductor structure. So superconductor, semiconductor, and superconductor junction. Okay. So this is actually going to replace your Josephson junction. So it is a combination, okay. But here you can see that instead of using Josephson junction, we use a semiconductor in between the in the Josephson junction. What you use? You have a semiconductor, and then insulator. And here, what you have then? Then you have a semiconductor, superconductor, and superconductor. And in this case, you're going to use a gate electrode. And this gate electrode is going to control the junction, this junction which is formed. So this gate is going to control the junction by application of some voltage. Okay, it is same like a transistor. it is a similar like a transistor. Okay, I hope you got the idea what we are doing here. A bit about different types of I can say qubit in the superconductor platform. Fine, shall we go ahead? So now see. So we want to understand in today's class, actually, I will be discussing about the one category that is called the charge qubit. And the structure will be something like this. First, maybe I will give you some overview so that you get the overall idea what is going on. So this is the Josephson junction, I will call JJ. And then there is a coupling capacitor. And this is and one more capacitor we use here. And this is going to be ground. And here then we apply some voltage that is called the VG. And this capacitor is called the CG capacitor. So, and this is called CS. So this is structure in the charge qubit. Josephson junction. So this cross in the box, I will call as a Josephson junction. Then there is a capacitor here, this capacitor. This is called the shunt capacitor. And then there's a coupling capacitor, or we can call as the gate capacitor. And then the voltage, some DC voltage here. And DC plus AC also going to apply later on. So I will show you that this whole circuit, okay, is simply going to act like a LC circuit or LC tank. And in the LC tank, then you will see that there are energy levels. And these energy levels I'm going to call as a 0 or at 1 or at 2. And these states I'm going to use as a bit or quantum bit. And I will show you that these qubits, okay, can be used to do all the stuffs which we have already discussed previously. But before we go into the details of the charge qubit, what we need here is a bit introduction, little bit, some idea about the superconductivity. Because without having, maybe what I will try that I will go very quickly now about the superconductors, and so that all the terms which I'm going to use, you become familiar with those terms. So a bit, or I can say a bit introduction about the superconductor. Quickly, I will not go into detail, but just I will brush up some certain or superconductivity. So you understand that it is a kind of material in which if you look at the resistivity, DC resistivity as a function of temperature, then the resistivity decreases linearly like in the metal. And then at a particular temperature that I can call as the TC, this at particular temperature TC, this is going to become 0. So a substance which shows this behavior, behavior means its resistivity becomes 0 at a finite temperature. So such materials are called superconducting materials. So resistivity becomes 0. Any idea how anybody can check whether resistivity is really become 0 or not? For example, let us say when you think about a niobium, okay? So niobium, the TC is around 9 Kelvin. It means if you cool down niobium below TC, then the niobium going to become a superconductor and the resistivity becomes 0. So let us say if you really want to check whether the resistivity is 0 or not, then you can just make a loop of this niobium wire and just pass some current in this. If the resistivity is 0, then this current will never go to decay. This current will always going to move for a infinite amount of time without any decay. So if you check this current maybe after 1 year or 1 light year also, or 100 light year or billion light year, still the current will still be flowing. Okay. And this flow current, which is flowing inside the loop because of this property. Okay. This is what is called the persistence current. We will be using these terms. That's why I'm just coining, doing or repeating these words in the class.
Is this the practical way or is it the theoretical? I mean,
It is a practical,
once
yes. It is a practical.
you apply a battery over this loop, and
Yeah.
so after applying the battery, so what? I mean, you just unplug the battery or it's keep on going?
You just unplug the battery and connect the wires together. Okay. You make a switch. Okay. Which switch
Okay.
is like you make a switch, correct? So that once the no current is start flowing, then just close it. Okay. And remove the battery. Battery you must disconnect. No, otherwise the battery will itself going to cause some resistance.
Hmm.
So then it will flow. It will not going to decay at all. This is what you see now in the MRI magnets.
Okay.
So in the MRI magnet, just they just charge this magnet, this coil once, okay, and then this keep working for years. They never charge it again. Okay, I mean they
Mhm.
charge practically, but because of the different reasons, but not because that the uh, because that the resistance is non-zero. Okay, because there's something called a quenching. So sometimes quenching takes place, then you have to charge it again. Okay. But this MRI, they just maybe you buy one MRI magnet in the, for example, in the, any hospital, and once
Hmm.
it is charged, oh, this will keep working, no, for no practically infinite amount of time. Okay, if doesn't quench,
So here also, if you have this rubidium, this will make it at 9 Kelvin pressure. So then this is a practical. Oh, I
it is a
thought that.
practical. It is a
Okay,
practical
thank you.
exactly. This will keep
Okay.
the current will keep flowing.
Mhm. Okay.
So in superconducting qubits, we use generally aluminum. And the aluminum TC is 1.2 Kelvin. So majority of the metals, they show this property. So one of them is aluminum. Just 1 minute. Yeah. So because this aluminum is of course, you can see that it is, I mean, if you're going to prefer other materials, so niobium generally people not prefer less because of it is not a very good metal at normal temperature. And aluminium is a very good, have a very good conductivity even in normal temperature also. So there's low losses. Okay. And it is a further very important aspect of the aluminium that when you expose the aluminium, okay, so this is going to make aluminium oxide. Majority of the oxides made on the metals, they are sometime mostly are behaving as an insulator. But this aluminum oxide, actually it is a it is a conducting in nature. So it doesn't create any kind of patch voltage. So people prefer to use the aluminum in comparison to the other materials. Okay. And of course, aluminum soft also, you can add any other properties. I mean, it's chemically stable, clean, easy to microfabricate. No, so those are the many other parts you can use, okay, to say that this is a very important material. But I can say this oxide is a very important now factor which is used. Because of that, aluminum is most preferably used. So aluminum naturally forms oxide layers. So there's no complicated steps are needed. Okay. So even in you can use this oxide which is formed as a part of the Josephson junction. So then there are many theories now of the superconductivity, and we can see that one of the important theory of the superconductivity is called the flux quantization. I mean, it will be good if you can study these superconductivity by yourself. I will be not uh, discussing all the parameters here. So what is the flux quantization means that if you take one superconducting loop, and then place this loop in the, let us say, external flux, then it is found that the flux which is passing through this empty region, I mean through this loop, and that flux I can call, let us say, phi. And it's very interesting that this flux is quantized. What I mean by quantized, that the flux, I mean, if you keep increasing this phi external, then the flux which is coming out of this loop is not increasing continuously. It will increase in steps. So this phi, that is the flux through this loop, is actually equal to n time phi naught. And this phi naught is what is called the fluxon, or you can say fluxoid. Technically, this is the flux quantum. And the value of this is actually h upon 2e. Sometime we also write in this format. For example, if you multiply with 2 pi and 2 pi, then it's also written like a h cross into 2 pi upon 2e. So this is another format. Now, the terms which I will use, for example, this h we call a Planck constant. Then this h cross is called reduced Planck constant. Similarly, here, this is called the flux quantum, the phi naught. But if I let us say phi naught by 2 pi, is like h cut is h upon 2 pi. So this is going to become h upon to E. So I can call this as the phi naught dash, this symbol. And this phi naught dash is called reduce.
Sir, this phi naught and phi external both are same or different?
Different.
Okay.
Reduce flux quantum. So when I say that this phi, so this phi is the flux passing through the through this loop, and this is actually equal to n time phi naught, and this n of course is going to vary like 1, 2, 3, and so on. In fact, it will start from it will take integer values, so it is go from n equal to 0, 1, 2. So I mean, so I avoid the using this word, but let us say just to make it clear. For example, think about here. On this side, you are applying phi external. On the y-axis, you measuring the phi. Then in normal situation, you think that this must go linearly, am I right? But this is not like that. What exactly how it varies? Like this way. So it remains 0 and then increases. Then again like this. So this is the kind of steps it follows. So for example, here I can say the flux passed here is the, let us say, phi naught. Here it will be a 2 time phi naught. Here it will be a 3 time phi naught and so on. So this is how the flux, I mean, on an average, if you look at, then this is following the same path, no? It is a going straight line, but in steps. So the flux is quantized. So when the flux is passing through the loop, so it's a quantized, and this is actually because of the flow of current here, that is called the persistence current. And so whenever you apply some flux from the outside, then you study in the Lenge's law in the EMT theory that when you apply, when you bring some kind of magnetic flux toward the loop, so when the flux start cutting, then this loop, Lenge's law itself is a principle, okay? So this says that this is going to oppose the very basic cause, and the basic cause is the increment of the flux. And to oppose this, what happens? There is a electromotive force in produce, and this electromotive force is going to produce move the charge electron in the loop, and the current will be in such a direction that another flux produce, which in this direction, and this flux and this flux, they will cancel each other. So it is going to, I mean, this is North Pole, also North Pole. So North Pole going to push each other. So this is the basic, I can say, fundamental rule in the nature that the system always going to oppose the basic cause. Okay. And you can see other way around. If you try to pull this magnet out, then flux will decrease. Okay. Now the system going to oppose the cause, and cause is that it is going away. Now what will do? Then the current direction will reverse, so that south pole become here. Then it try to pull the magnet. So this is what happening here. So when you try to apply a flux here, so this flux is passing through the loop. So here, again, the Lenge's law is applies here. So in order to cancel this flux, a current is going to flow on the surface, and this current direction will be such that one kind of flux is produced. Okay, and this flux is going to cancel this flux. But of course, this current cannot exceed the critical current, and beyond that, it will again reset. Okay, and this is the reason that again the flux will going to increase in the stepwise. So I mean, I will avoid to going deep into this study, because then we will deviate from our major task. But this is how one concept is what is called the flux quantization in the superconductivity, very important for us to understand here. All right, clear this part?
Sir, how this IP means persistent current, it changes with phi external. It is also in stepwise.
It will keep increasing because if the flux is increasing, then in order
Is
to
it linear?
increase the, yes, in that sense is linear because this is, let us say, phi SC, okay? So phi SC is produced because of the IP. So this phi SC and this is going to cancel the phi external. So this IP will increase linearly, increase in such a way that the phi SC becomes equal to the phi external. Then only the flux will be cancelled. But this IP, if you keep increasing the flux phi external, this IP will keep increasing. But remember, this IP cannot exceed the certain value, no? Critical current, because after that, this system itself going to destroy. Then it is more of quantum mechanical concept, but I think better that we should not divert our not study too much in this category or this type. But just true, this IP will keep increasing. Okay, fine. Shall we go ahead?
Yes, sir. And one more thing about that superconducting, that critical temperature. So on
Mhm.
that temperature, generally Cooper pair produced, and
Yes, exactly.
since they don't interact with the systems, they move freely. But
Exactly.
my question, why they don't interact? Is there any reason?
Oh, yes. There is a very strong reason, okay, that why they don't interact, okay. The reason is that, first of all, these Cooper pairs are bosons, okay. And because of bosonic nature, they are not bound to follow the Pauli exclusion principle. And for example, in the metal, if you have electrons, large number of electrons, then these electrons, they keep moving in the random direction. And because they cannot no, stay in the same quantum state, so their wave function cannot overlap. So each electrons are governed by different wave function. And because of Pauli exclusion principle, they cannot come very close, because then their wave function will start overlapping, and this is not allowed by the Pauli principle. Whereas when the two electrons are going to make a Cooper pair, you can see that their spin orientations are opposite, correct? So the net spin of the system becomes 0. So they are actually boson. So Cooper pair itself is a boson, so they're not bound to follow the Pauli exclusion principle. It means all the Cooper pairs, in principle, they can stay in the same quantum state. So for example, let us say two Cooper pairs, if they are formed, so of course they are governed by a single wave function because they are Cooper pairs, okay? And another Cooper pair comes, okay? Then if they can stay in the same quantum state. So if they are staying in the same quantum state, that is this wave function. So another Cooper pair comes here, and you can see that its wave function will overlap. And they are governed by a single wave function, large, giant wave function.
So then
And as a result,
how do you say it's this excess Cooper pair from here? I cannot relate from here to excess Cooper pair.
excess Cooper pair means?
Means at the beginning you told there is a
Okay,
more.
please don't try to
Okay.
right now. Let's not mix that one. Okay, I'm just
Okay,
discussing here
fine then.
I'm answering your question. Okay, so we
Okay,
will
fine,
come to
fine,
that
sure.
access. Okay, so here you
Sure.
can see if more Cooper pairs are now coming in the same quantum state. Okay, then this wave function become bigger, bigger, and bigger. Okay, so you can see that ultimately all the states, all this Cooper pair, they are governed by a single wave function. And for example, in the case of metal, electrons are independent, so they're going to collide with the phonons easily. So this is phonons, let us say. and electrons, they will have a collision. So when the electrons, phonons collide, they will scatter. But look at here, in the case of a Cooper pair, these collective state of Cooper pair, no, that is called the Bose-Einstein condensate. So this collective state is going to move collectively, correct? It will not be possible that one Cooper pair go this way, other Cooper pair go this way, because they are governed by a single wave function. Are you getting?
Yes, sir.
So when they are moving in the collective sense, okay, so this is a big, even you think classically also, is a big structure, no? Let's say you have millions of electrons moving together, okay? So think about one electron and one phonons. If they collide, okay, so electron after collision goes this way, phonon goes this way. But now think about there is a collision of phonon with this cluster of millions of electrons. Now you can see when the collision takes place, what will happen? Which particle will going to scatter? Tell me.
Here both are bosons, right?
Both are bosons, but think about this boson in nothing but millions of particles together. Okay,
Mhm.
is a bulky system. It is something like you if you take no analogy, then let's say you have one car, another car, they collide, and one goes like this way. But imagine if you have a large number of cars, and then you make a together, okay, and then small car. If they collide, what will happen?
Obviously, this small curve will go and
Exactly, nothing happened to the big one, correct?
it's like a football hitting a wall kind of thing.
So think about like a tank, okay, a tank hitting a car, okay. Military tank is a bulky structure, 1,000-ton heavy structure, hitting a car, maybe just 200, 300 kilograms a car. Okay. So you know that this military tank, nothing happened to the tank, only the car will going to deviate. This is what exactly happened. I'm taking analogy on it to let you understand why these phonons, you say Cooper pair never interact, because when they're moving, okay, they make their own path. Okay. These phonons, they never going to cause any damage or any kind of momentum transfer to the this particle, a big cluster of the no. That's why you can see the resistivity suddenly becomes zero, even at a finite temperature, because at this temperature, these phonons not going to cause any resistivity. I hope it's clear.
Yes, sir. Please go on.
Good. So I said in the flux quantization, with the terms which you need to understand is a phi, okay, and this phi I call phi naught, and another term and phi naught is h upon 2e. Another term called phi naught dash, that is the h cross upon 2e. So just keep in mind that these are the terms we have. Now, coming to the our task. Now, let's not go too much into the superconductivity. You can study yourself. Now, think about superconducting quantum harmonic oscillator. So I will just take a, let's say, aluminum wire, okay, and I will just make an aluminum wire, and I will make a, let us say, inductor like this way, and then I will take one capacitor and I will attach it. So the capacitance and the inductance you will be having here, and I can just think about that. I can just make a some charge I can produce on the capacitor. Then you can see when the capacitor going to discharge, then this current is going to flow through the inductor, and as a result, in the inductor, then there will be a flux going to produce, which I can call phi. And then this current will go this way, and this plate going to charge. And again, this going to discharge, and then current will reverse. And you can see that this way, here, the current is going to oscillate. Okay. So this is the typical LC oscillator. So at one time, when the capacitor will completely charge, then the energy is going to be stored as a UC, that is called as the Q square by 2C, correct? I hope it's clear, this concept, and no need to discuss. So this is the energy stored in the capacitor, correct? Energy stored in capacitor. So this is LC oscillator. And here the energy is going to oscillate back and forth between the capacitor and the inductor. And similarly, energy stored in the inductor. I can call as a UL. And how to write down? 1 by 2 times L I square. Now see, the magnetic flux through inductor is how much? L time I. So you can see that with this logic, I can just calculate the I value. So this is going to be a phi upon L, and you can put here. So this UL becomes simply a phi square upon 2L. So the total energy of the LC circuit, let's call the U total, is going to be electrostatic energy, energy stored in the capacitor, energy stored in the inductor, nothing but a Q square upon 2C plus phi square upon 2L. Now, what we want to do here, we want to solve this LC oscillator quantum mechanically. Because you can see that this whole system, this whole oscillator, quantum qubits, they're going to cool down to around 10 millikelvin. And in 10 millikelvin, you will be accessing the lowest energy levels where the quantum observations are more prominent. So what I want to do, I can convert this into quantum mechanical Hamiltonian. So using this classical result, I can write down the Hamiltonian for the quantum version of the LC circuit. So let's go for the Hamiltonian. For the quantum version of LC circuit. So what I will do, I will just now convert these observables into operator form. So charge is a observable which you can measure physically. You can measure. So it is a observable. Flux is also observable. You can physically measure this quantity. So it is observable. So when you're going to convert into quantum, you're going to write down the corresponding quantum Hamiltonian. Then what we do, we just replace this observable to the corresponding quantum operator. So this Q is going to become a Q cap. No? The Q cap is the operator corresponding to the observable charge. And of course, this is the 2C, and corresponding flux I can convert, upgrade to a flux quantum operator. Be careful, be attentive and careful that Q cap is not equal to Q. Similarly, phi cap is not equal to phi. Okay. It is same like in the quantum mechanics when I say momentum is not equal to momentum operator, because momentum is a physical quantity. Okay. Is a physical quantity whose units are kilogram meter per second. But this momentum operator is an operator iota h cut del by del x. This is a mathematical operator. Okay. This P is not equal to this P. That's why you use this cap or hat at the top. Okay. So keep in mind that these two are different things. Okay. This P cap is a symbol of the operator. But when you operate this operator on the state, then, and this state, let us say, is an eigenstate of the quantum operator P, then it will going to give you the momentum value. So this is the momentum physical value. Okay. So just keep in mind that this Q hat and phi hat, they are not exactly they are not the charge or the flux. They are the corresponding quantum operator. And what we want to do, we want to solve this Schrodinger equation, or time independent Schrodinger equation, to calculate the energy eigen states and energy eigenvalues. So I can solve this equation. So what we're going to, it is Q square here. So what you can going to see here is Q square upon 2C plus phi square upon 2L. And this is the quantum state psi, and this is the E psi. So this is the Schrodinger equation for the LC oscillator. You can compare this. No, you can compare this with our spring mass oscillator, spring constant K and the mass M. And for the spring mass oscillator, what is the Hamiltonian or this equation, quantum mechanical equation, P square by 2M plus 1 by 2 time Kx square into psi and E psi. You can see that our physical, no, I mean, quantum harmonic oscillator, let us say, having a spring constant K and the mass M. So when the particle is in the potential box, a harmonic potential box, then the Hamiltonian written in this format. So you can see that Hamiltonian, this Hamiltonian, they are same. And here you can make a comparison, no? So it means they are same. It means the momentum. So momentum in our operator is equivalent to the charge here. So I mean, if I write down, this is a simple harmonic oscillator and this is the LC circuit. Then the Hamiltonian here is nothing but a P square by 2M plus 1 by 2 time Kx square. And here Hamiltonian will be a Q square by 2C plus phi square by 2L. The first thing. The second is the momentum means here nothing but a Q here, charge. Third, when I say X cap, so X cap nothing but phi cap here. When I talk about a mass here, what is the mass here? Can you tell me?
Capacitance.
Is the capacitance correct? And 5, the K, spring constant, equal to 1 by L. It means, for example, if I define momentum operator like minus iota h cut del by del x. So here I can define Q operator like minus iota h cut. Now this is x, so it will be del by del phi. You think about omega naught, that is 1 upon square root of k by m. And here omega naught will be, if you put k by m, this is going to be a square root of LC. So we have a parallel representation here. Now, what my goal is to let you understand. See, we have this Schrodinger equation, and now I see I can write this Q operator in this format also. So it means this equation can be also written like this format. Let's say minus h cut square by 2c and del square upon del phi square plus it will be a phi square by 2l into psi and E psi. So you can see this is the kinetic energy term and this is the potential energy term. So potential energy, let me call U phi. So this U phi is what? Nothing but a phi square by 2L. So I'm using all these very basic things because I don't want you to get confused when I'm going to use these terms later on to understand the charge qubit. And for example, here, when you talk about energy, so energy is nothing but a n plus half h cut omega. So same logic you can apply here also. So the energy here will be equal to again n plus half h cut omega naught. And what you see here is the following, that this LC oscillator is actually going to act like a harmonic oscillator. And in this, there will be different states correspond to n values. So for example, you can have a 1 by 2 h cut omega naught. So this correspond to a state. Let me call 0. Next state will be a 3 by 2 h cut omega naught. Similarly, you can call it as the 1 and 2 and so on. And you can see that these states are equally spaced. The spacing here is what? H cut omega, H cut omega, and H cut omega. And there is a problem. Now you can see. The problem here is that if I'm going to use, let us say, this 2 state as a qubit 1, so if I'm going to use this as a qubits, and if I'm going to, let us say, excite qubit by shining some microwave of energy h cut omega, then the transition from 0 to 1, of course, will take place. And now the system will be in the 1 state. And now I want this to come back to 0. So again, I will shine another photon. But in this case, so that it can stimulate, but in this case, there are 2 possibilities. It can come down, no doubt, but it can go up also, because this gap is also a h cut omega. So this is a very big problem in this system. So if the energy levels are equally spaced, then I can not make a reliable quantum computer, because in that case, accessing 2 levels will be challenging and very difficult. Clear this part? So what we need, okay? So technically, we can see that what we need this kind of oscillator, where these energy levels are not equally spaced, but they are decreasing like this way. So you have a 0 here and 1 here and 2 here, and you can see these levels are different. So if I shine, let us say, photon correspond to this energy, so this will never going to cause transition from 1 to 2. So that is the goal. This is what we want. We want an harmonic oscillator, LC oscillator, and not a harmonic oscillator. Is this clear up till here? Any question? Anybody want to ask?
Yeah, hello, Sugam.
Yes.
So regarding the correspondence between the Schrodinger equation and this equation that we
Yes.
wrote. So here in this case, the wave function of what are we talking about? Is it again a Cooper pair or what wave function are we talking about here?
So it depends on what actually variable you're going to use to create a qubit. For example, if I'm using a charge, okay,
Mhm.
charge as a qubit, okay, excess charge. So one charge is extra, other charge is less. Okay, so let us say I will say either 0 charge or 1 charge. So in this situation, the wave function, okay, the wave function is going to be a wave function of the Cooper pair. If you're going to use the, let us say, a flux, okay, so in the case of the flux, still the wave function will be Cooper pair, or wave function of Cooper pair, but the variable will be the flux, variable will be the, in the case of phase, it will still remain the wave function of Cooper pair, but the variable will be the phase of that wave function. So in one line, I can say that the wave function of the Cooper pair will be, that is the psi here, which of course you can write now, like for a superconducting system, generally how do you write now? Like ns and e power iota phi. So this is how we represent the wave function of a Cooper pair.
Yeah. Only difference with the electronic system may be that this is following probably the symmetric wave function, no? Like
Yes, that's true. Yeah,
the pairs.
that's correct. That's correct.
Yeah.
Yep. Okay, so our goal is very clear that we want to make n-harmonicity, we want to create n-harmonicity in the system. And before we go into that part, let me also simplify this equation further in another form. So for example, I said this q square upon 2c plus phi square by 2l, this psi equal to e psi, and this is also equal to minus h cut square by 2c and del square by del phi square and plus phi square by 2l into psi equal to e psi. Now, I'm going to introduce some terms here. No? So the one term, some new terms I'm going to introduce. So one term I'm called EC. This is called single energy, sorry, single electron charging energy. So for example, in a capacitor, you have, if you want to add one electron on the capacitor, then how much energy is required for that purpose? Okay, so that is the what term I can use as the EC, that is going to call as the single electron charging energy. So this is same like a no, think like a this UC, how you define? Q square by 2C. So this is the energy of the capacitor when you're going to store Q amount of charge. But here simply, if the Q is, let us say, only a single charge, let us say E, then in that sense, then this UC is simply become the EC, and the equation become a E square by 2C. So this is the term I'm going to use as a single electron charging energy, because finally I'm going to go to the single qubits, okay, or single Cooper pair. So we will use this term. And another terms I will use that they call ECC. That is the single Cooper pair charging energy. So it is simple, because when you talk about Cooper pair, so charge is how much? 2E. So this is going to be a 2E whole square upon 2C. So you can see that this is simply become 2E square upon C. So these terms we will use. And you can see that if you really want to write in term of single, so this is going to be a 4 time EC. Now, another term, let us say N, or maybe I can say small n, that is the number of Cooper pair on the capacitor. So I want to write down everything now in the n form now. So you can see that this Q will become what? This become n time 2E. And from there, you can see this n is going to become then Q by 2E. And from there, this UC, that is simply nothing but a Q square by 2C. So you can see that this term become what? You can see Q here. So you can put the Q. So this is going to become then n square and 4E square upon 2C. And that is going to become 4n square into EC. So this equation we will need frequently 4 times EC into n square. So I'm still discussing in term of a single electron charging energy. Okay. चाहो तो इसको ऐसे लिख सकते हो, UC will be equal to ECC n square also. Both the terms are valid. I mean, one in term of a single Cooper pair charging energy, and this one is the single electron charging energy. But we will prefer to write the in term of EC. Okay. So you can see that I have written this UC in this term. And further, one more line you can add. Sometime it is more convenient to use the superconducting phase. superconducting phase and as a variable, superconducting phase as quantum variable. I mean, in this wave function, when I write like this equation, iota phi, so this phi is what is called the superconducting phase. I will talk about further. So one more I will discuss later on in Josephson junction. Maybe just a few minutes later I will discuss. There are two relations. They are called the Josephson's relations. So the first relation is I equal to I naught sine phi. So this actually relates current versus phase, current versus phase. And a second relation says V equal to I naught by 2 pi and d phi by dt. So this relate voltage versus phi. So they are the two Josephson relations. And we will talk about, I mean, this one you can also written like a V equal to phi naught dash also, okay, and d phi by dt. In fact, if you take this term inside, then this is going to become d into d phi naught dash and phi upon dt. And this must be equal to phase. So you can see this is what is called the d phi upon dt. So here you can see another very important relation that I mean the voltage. No, you can you know that I mean so in our the voltage and the flux, this is how they relate each other. So simply I can define that the flux is actually equal to flux on into phi. So this is also going to be used, or maybe equally you can write like this way, phi equal to phi naught upon 2 pi into phi. So somewhere I will use the phi dash, somewhere I can use the phi naught. So this phi naught is called reduce flux quantum. And this is simply called flux. So this equation you can keep. And now you can look at here. I want to write the Schrodinger equation in terms of phi, not phase in terms of phase. So what I can do, I can go back to Q, this equation, look at iota h cut del by del phi. And here you already know that Q is nothing but a n time 2e, and this phi nothing but a, you can see here already. So this is actually this is a phi naught upon 2 pi into phi. So you can put here in this equation, you can solve yourself, and I can tell you, you will get this equation n cap equal to minus iota and del by del phi. So you can see this n number, okay? This was the number here, number of Cooper pairs. So I'm going to use this as a number operator. So this is going to call as the number operator. I hope you are very much familiar in the quantum harmonic oscillator about the number operator. And now if you look at the Schrodinger equation, or maybe I can little bit modify this UC. which was nothing but a minus h cut square by 2c and del square by del phi square. So here you can put the value of phi and try to solve it. I can assure you, you will at the end, you will going to get minus 4 e square by 2c and del square by del phi square. Nothing but minus 4 times EC. This is the EC, that is the del square by del phi square. So you see that this UC is written like a minus 4 times EC and del square by del phi square. So one equation in terms of phi. Similarly, this UL, the energy in the inductor, no, that is equal to phi square by 2L. If I put the value of phi naught, that is the phi naught upon 2 pi and whole square uh, also equal to, equal to phi whole square upon 2L, then you can see that from there you can get another energy that is called the UL will be equal to, let me call phi naught by 2 pi whole square, and here is the phi square upon 2L. What I can do, the way I define EC, I can define here one more term that is called the EL. So this become 1 by 2 times EL into phi square. So this is going to become 1 by 2 times EL into phi square. So you can see that UC and the UL written in this format, and this EL nothing but phi naught upon 2 pi whole square into 1 upon E. So this term is called inductive energy. We will use this. Even you can write like this way, no? Phi naught dash whole square divided by L. So what you need to understand that these are the two equations you have, and here this EC. EC is what? E square by 2C, and EL nothing but a phi naught dash square upon L. So these terms you can use, and now you can see the Hamiltonian is going to become then minus, which is actually minus h cut square by 2c, and this was equal to del phi square plus phi square by 2L, which are nothing but a UC plus UL, and you can see that now this is going to modify, and this becomes now minus 4 EC and del square upon del phi square plus the second part. Okay. The second part either write in this format, 1 by 2 EL into phi square. And this omega naught
One
then,
second, I am interrupting. What is the EL? The energy EL?
this energy EL is termed as a inductive energy.
Inductive energy. Okay.
Yes. And this omega naught, which is defined like LC. Okay. So since L from here and C from here, you can put here, and I can tell you this is going to become then square root of 8 EC and EL divided by h cut. Just record it, keep it in somewhere in your notebook. I mean, you can see that it depends. No, for example, if I took capacitor, let us say around 10 picofarad, and inductance, let us say I take around 25 nanohenry, then I can calculate this EC. This is going to very small energy, around 10 to the power minus 24 joule. You can calculate in the EV also. And this EL also, you can calculate, that is going to be a 4.29 10 to the power minus 24 joule. And from there you can see omega naught. It is going to be 2 pi into 10 gigahertz. So here you can see the frequency is 10 gigahertz. And if you calculate the energy h nu and compare with the kBT, and from there you find temperature. So temperature comes out to be 500 millikelvin. It means that this separation which I was talking about. So look at here. So this is also equal to E equal to h cut omega. So this separation which we're talking about, this separation, that is the h cross omega. The corresponding frequency is only 10 gigahertz and temperature is 500 millikelvin. It means, what it means, if I put temperature, let us say 1000 or maybe let us say 1 Kelvin, then this temperature is much more than this temperature. Energy become higher. Then this is going to cause this spin, this qubit from 0 state to flip itself into the 1 state, or 1 state to come into the 0 state. Okay, so this is something you don't want to do. That's why you have to cool down the whole system. In this case where the you took capacitance around 10 picofarad and inductance around 25 nanohenry. So for this system, you have to cool down the system below 500 millikelvin. Then only the system is going to behave now in the better way. But this is very high, I can say, capacitance. Okay. Technically, when you come, I will come to the when I come to this qubit, real qubits, then this capacitance is going to be around 10 to the power minus 15 farad, very small capacitance. And in that situation, the temperature further reduce. Well, so I have discussed this, and I told you that the energy levels are there, and this energy levels are now going to cause problems. The separation between the energy levels are equal, and this equal separation is going to create a problem, because if I going to shine photons, then all transitions will take place, which is not advisable. So what I need to do, I need to make this system anharmonic. So question that, how to make anharmonic LC oscillator. So this is done by adding Josephson junction in the circuit. So I will show you that if you add one Josephson junction in the circuit, so this Josephson junction is going to actually replace this inductor. So see, because of this system, you are getting energy equally spaced. And because of, and this is actually a harmonic oscillator. And I will tell you, in this situation, energy is no longer delta E no longer equally spaced. And this system is called an harmonic oscillator. What I mean to say that in this system, the potential is like this, equally spaced line. In this system, I will show you the potential like this. So here, the levels are going to decrease. Here, the potential is proportional to x square. Means in our term, proportional to phi square. But for example, when you talk an harmonic oscillator, so the potential is not only proportional to x square, but also proportional to x cube, or maybe you can see proportional to x, x square, x cube, and so on. So I mean here, it will be proportional to phi also, phi square also, and so on. And this is what I will show you, that when you add Josephson junction in the circuit, then this is going to make the circuit an harmonic oscillator. And then we can use this for our purpose then. Clear? Objective clear to everybody what we are doing? So before that, let us prove that. So let's prove that Josephson junction creates non-linear inductance. So see, when I talk about Josephson junction, so I think a little bit talk about this because this is something we're going to use. So it is nothing but a superconductor. So here superconductor, and insulator. So this superconductor made of aluminium. This is also made of aluminium. And this insulator is made of, let us say, aluminium oxide. Is alumina. Okay. So what happens that Josephson, he no, came out with a theory, and he said that when you go into sandwich, and if the thickness of this insulator is of the order of nanometers, then what he found that the Cooper pairs from the one region, they can tunnel into the second region. And here, this wave function of the Cooper pair is actually a ns e power iota phi 1. And here I can call psi 2 ns e power iota phi 2. So there is a tunneling of Cooper pairs across the superconductor, insulator, superconductor Josephson junction. And when you're going to plot the wave function, its magnitude is going to plot, it will decay. So it is like this way, and then in this, it is going to decay exponentially and then remains constant. That is the psi here. Same thing on this side also, and decay. that is called the you can call as the phase difference, or sometime also called superconducting phase, or sometime also called phase of Josephson junction. And if you think about why this Cooper pairs are tunneling, okay, so a super pairs tunnel, okay, and he also found that this current, okay, which is because is produced because of the tunneling of the charge carrier, this current will be equal to I naught into sine phi. So phi is given here already. So where this you can see this I naught is the maximum super current, that can pass through the junction, or maximum super current across the junction before the onset of resistive state. Resistive state means normal metal. Means this situation comes when the I is become more than I naught. And this is called super current, maximum current, or critical current. And this critical current depends upon on the material. Okay, so it depends upon what is the band gap in the superconducting material. Okay, what is the junction now area and thickness. So all these parts it will depend. Okay, and generally this current, this is called a zero voltage sorry, this is called a current phase relation, and this is called zero voltage state. So you can see that if you look at a little bit, go further deep into why these charges are flowing. Okay, so the cause is because of the phase difference. You can see when phi is 0, so I will be 0, no current is flowing. So this indicates that the phase difference causes the tunneling of Cooper pair. So if there is a phase difference, then only the Cooper pair going to tunnel. Can somebody will like to give me why this happens? Why the phase difference play a role here? See, when the phi is non-zero, means the phase of the two wave functions are different. And in this situation, or you can see when, let us say, when the phi is 0, when the phi is 0, so in this situation, I can say the Cooper pairs, okay, or the wave functions are or Cooper pairs are in maximum coherence. So there is a no push for current or for tunneling. But when phi becomes non-zero, then I can say the system reacts by pushing. I'm giving some analogy, pushing Cooper pair across Josephson junction. So whenever there is a phase difference, then only the push will take place and then the Cooper pair will tunnel. You can think, I mean, so if you're facing some problem, then you can think like now, how can, okay, think about like two swings. Now, if the two swings are attached together, just try to think about if the both swings are attached together and if they are oscillating in the same phase. Same phase means when it becomes maximum, it also goes to maximum. It means the phase difference between both is 0. Now, can you tell me, will there be any energy transferred between the two oscillators? Hmm? Are you getting what I'm trying to convey here? If these two oscillators are oscillating in sync, no? Sync means ki if they are at the vertically down, then they will be at the same time. If they go here, they go at the same time. When they come here, they come at the same time. So in this situation, you can see that there will be a, or maybe if you're feeling that not this way, there can be some separation comes. Think about that this pendulum is going in and out of the board. Okay. Then in this situation, this length L will never change. Correct? Now it's clear.
It's okay, sir.
But let us say that if situation comes different, that if the one particle is here and one is here, so definitely you can see that when it means that when one goes on this side, other also goes this side. So in that sense, this length is going to play a role. So when they're out of sync, then you can see that there will be energy transferred, correct? Or maybe you can think like this way, there's a one oscillator is oscillating and other oscillator is the rest and they are connected. So only one is oscillating. What will happen? This also going to oscillate now slowly. So you can see the energy will be transferred. So only the phase difference when there, then only the energy will be transferred. Other also going to move. This is what exactly happens in the here also. When the phase differences between the two wave functions on the left and the right side, when they are different, then only energy transfer will take place. Then only the Cooper we are going to tunnel. So the energy transfer will start taking place only when the phase difference is there. And this is what is happening in the case of a Josephson junction. Please, any question up till here? Yes. Shall we go ahead then?
Yes, sir.
Good. Now we are discussing still Josephson junction, and our goal is now think about. Our goal is to make the system anharmonic, and for this one I am adding the Josephson junction. And here I want to prove that Josephson junction actually is going to create a non-linear inductive energy. So for this one, let us try to little bit work more. So I said that there is the first equation. So first equation is called I equal to I naught and sine phi. There is a second equation also, which one can prove by the Schrodinger equation. And the second equation is called V equal to phi naught dash and d phi by dt. So first is called the current phase relation and second is called the voltage phase relation. Both these Josephson relations can be derived by solving the Schrodinger equation with an overlap of the wave functions, okay, from the both side. So this is the mathematics. You can go and check how to derive these both equations, but I'm going to use it. And I further said that this state is called a zero voltage state. Why I'm saying zero voltage state? Because there's no applied voltage. So when there's no applied voltage, then you can see here, if I plot voltage on this side and current on this side, okay, then this I, okay, so this I is going to be like this, okay. So up till here, this will be I naught, that is critical current. That is a 2 delta by E. And above this, if you go further above this current, then it become normal conductor. And there the system, or maybe I can do the same like this way. So it will follow the normal IV curve. So, but here it is the normal metal.
Sir, what is the significance of the capital D 2D by into D by E?
Capital?
Capital D 2 delta by E or 2D by E. There is.
Okay, this one, right?
Yes, yes, yes.
So this 2 delta is called EG, and this is called the energy
Gap, band gap
exact energy gap of
between superconducting and the normal.
no, only superconducting. Exactly, superconducting. You can say Cooper pairs and normal electrons.
Okay, okay.
So here, what if I apply some voltage? Let us say if I apply some voltage. So superconductor I and I. Now, if I apply some voltage V, then what will happen? Okay. So in this situation, what I can see, I can if a constant voltage applied, then I can solve this equation, equation number 2. And from there, you can see this d phi by dt. This is a phase actually. This is going to become V upon phi naught dash. This also equal to 2 pi upon phi naught into V. If I integrate, first let us not take this d phi there. So this is the d phi equal to 2 pi upon, and of course, you can see also this phi naught is what? H upon 2 E, no? And so this is going to become then, it is simply going to become a 2E upon H cross and V into dt. And now I can integrate. And from there, you can see that if you integrate and solve, then you will get phase equal to phase naught plus 2E upon H cut into Vt. And this I can put here. And you can see that the current is going to become then I naught into sine and phi naught plus 2E upon H cut into Vt. This phi naught is nothing but simply at T0, the phase equal to phi naught. Just keep in mind. So this is what is no, I mean, so you can see the first is called this one is called a DC Josephson effect, and this is called a AC Josephson effect. So you can see that in the case of AC, when you apply some voltage, then the current will oscillate. The Cooper pair will go there and come back. Okay. So the Cooper pair will keep oscillating. So this is how this, what is the frequency of oscillation? You also can calculate I naught into sine. You can say phi naught plus omega t. So that's the frequency of oscillation, which is nothing but a 2 EV upon h cut. When you solve it, it is actually 2 pi time 483.6 gigahertz per millivolt. So this is Josephson junction, okay, and this is the current equation which we got. Now coming to one thing that since too much mathematics is needed to discuss here, I have to extend my class today for some more time. Fine. We are coming to the very close to understand that how the charge qubit superconducting quantum computer works. But to reach that, I need around 20 more minutes. Is it fine?
Yes, sir.
Okay, thank you. So you see here, when I talk about a Josephson junction, so there is a superconductor, insulator, superconductor. Okay, so technically here charge are flowing. So this part, this is also acting like a capacitor. So the first thing I'm going to now prove that this energy or inductive energy is non-linear in the case of a Josephson junction. So for that one, first of all, let's work about Josephson capacitance. So Josephson junction is like a parallel plate capacitor, and therefore it exhibits capacitance. And how you can calculate? That is the capacitance is Cj. So this is going to be directly constant time epsilon naught A by D. This is the way we calculate the capacitance, where of course you can think like this. So that is the area, and this is the junction thickness, and K is of course is the dielectric constant of alumina. Further, another point, please note down. This Josephson junction is going to also look at when you talk about this voltage applied. Okay, then you can see that, or maybe you can write down line here. Or maybe I can say it is going to also act like a inductor. So Josephson inductance. And to understand, I mean, capacitance is very simple to understand. To understand the inductance, let me dictate something. Uh, if you look at the Josephson equations, no relations, equation number 1, equation number 2, and look at the phase. Okay, so when the phase is changing in this, so change in the phase going to cause change in the current. And if the phase changing with time, then this is going to cause a voltage drop. So this is a point I want to mention here, that if there is a d phi by dt, then this is going to cause, that is going to cause a voltage drop. And also this I equal to I naught into sine phi. So since the Josephson relation indicates that if the phi is changing with time, then there will be this is going to cause a finite voltage across the Josephson junction. Therefore, I can say that this Josephson junction is actually going to behave like an inductance. And how I can find the inductance value then? What I can do, I have this equation, I can differentiate. Look at here, I will it become d by dt. Now phi is a variable, okay? So phi here is a variable. So it will become V naught into cos phi, then d phi by dt. But this d phi by dt, this d phi by dt already you know, this is equal to what? V upon phi naught dash. So you can put here, so this is going to become I naught into cos phi into V upon phi naught dash. Further, let's simplify. This is going to become I naught into cos phi. And what is the phi naught dash? This is equal to h cut upon 2e. So put this value. So this is going to become then 2ev upon h cut. And from there, you can see that the di by dt actually becomes 2ev upon h bar into I naught into cos phi. And from there, I can find the voltage. This is going to become h bar upon twice e. Then I naught and cos phi into di by dt. This is the equation which I can compare with the di by this equation. So when you have an inductor, and when you across the inductor, so here you have an inductor, and if the current is varying, okay, so that change in the current is going to produce a voltage. It means if you compare here, then this equation I can write like a V equal to Lj into di by dt. And here this Lj, which is nothing but h cut by 2e I naught into cos phi. This term is called inductance or Josephson junction. Or sometime we can make it like this way also. Let us say L J naught. So all the constant terms I can club together and cos phi. Where this Lj naught is actually equal to h cut by 2e upon 1 upon I naught. So nothing but you can see phi naught dash upon I naught. So you can see now, so if you compare, so you can see that Josephson junction is going to also behave like an inductor. It also going to behave like a capacitor. So here, if I have a, let us say, insulator, superconductor, then I'm going to show this as this box with a cross, but this is in fact actually equal to, I will show one cross here like this, and then one capacitor here. And I will call this capacitor as Cj, and I will call this as the Lj. And Cj and the Lj already you know from this equation. So I think everybody is convinced that Josephson junction is actually behaves like a parallel capacitor and inductor. Is this clear to everybody? Or do you want to ask any question? And now things are very simple now for us, because I have shown that this Josephson junction is behaving like a parallel capacitor and inductance. So what I can do, I can calculate the potential energy of a Josephson junction, because that energy, you can see that, is going to add up, no? So you have already this U proportional to phi square. And if I add something like a phi or non-linear function, then the potential energy become anharmonic. So I need to calculate the potential energy. So how you can calculate? So if a current is flowing, so let us say if the current I is flowing through this junction with a potential drop of V, then the energy is going to stored in the junction. And this energy I can call as the Uj. And this Uj is simply, I can integrate the power, very simple basic formula. And this is going to be I into V into dt. And look at here, I can put the values. So when this is time, then time. When I go for the, let's put here I. So I is what? I naught into sine phi. And what is the voltage? So voltage nothing but a, look at above equation. So we have a phi naught dash and d phi by dt into dt. Now you can see that dt cancel out. So technically this is actually with respect to phase only. And here it will be a I naught and phi naught dash and 0 to phi into sine phi into d phi. And this is going to become I naught and phi naught dash. This is going to become cos phi with a minus sign, 0 to phi. And further one more step, and we are here already. This is going to become then Ej 1 minus cos phi. So this is the energy stored in the inductor. Where this whole part I'm calling as the Ej. So this Ej nothing but a I naught and phi naught dash, and this is called Josephson energy, or sometime we call Josephson coupling energy. So technically this Ej arises due to the overlap of the or coupling of the wave function on the both side of the superconductor. And here you can just think that this Ej is just a constant, is energy offset. So this is going to simply shift the energy scale. Nothing more than that. So we can drop it. I mean, just to make the equation simple, we can drop it. And in that situation, then this Uj is going to become simply minus Ej and cos phi. And now imagine that you have one inductor coming through the Josephson junction, and then you apply a capacitor here. Let it the C, and this this is the C, and in this look carefully, then this is nothing but equal to a one inductor and one Cj and Lj. And let it call this CS, or maybe C only. So you can see now in this case, this H Hamiltonian will be going to be UC plus UJ now, correct? And this is equal to minus 4 times EC and del square upon del phi square. And this is going to become minus EJ and cos phi. Look at here, we are already done. So when you had a normal inductor and a capacitor, so in this case, this H was what? Minus 4 EC and del square del phi square, plus it was a phi square by 2L, correct?
Phi square by 2L.
So it was like a minus H cut square del square upon del x square plus 1 by 2 kx square. So in this situation, you can see the potential was perfectly parabolic. But here, look at now, instead of phi square, what do you have? Cos phi, correct? And if you look at the cos phi, when you do a Taylor expansion, cos phi ka, so how I can write down? Cos phi equal to 1 minus
Phi square by 2 factorial
phi square by 2 factorial
plus phi 4 by 4 factorial. It's phi 6.
Can you
Oh,
see that all the components are there, correct? No doubt this component will going to cause perfect parabolic potential.
parabolic.
But this one, this will going to cause deviation, correct?
Yes.
From parabola. As a result, in this case, you can see that the potential is going to be like this way. So in this case, the potential is going to be like this way. And of course, in this case, you will see the energy levels are equally spaced. And when you're going to solve here, then you will see that the energy levels are decreasing slowly. I mean, this can be done now by we should solve this H psi equal to E psi. I will solve it. Of course, not today, okay, but we will solve and we will see that when you solve this energy, then I will get the energy eigenvalue. And that energy eigenvalue not going to give us the equally spaced lines. And remember that this Schrodinger equation, which you get here, okay, this is a very special name that is called the Matthew equation. So which is include this non-linear energy. So because of this non-linear energy, that is a cost dependent. Okay, the potential becomes anharmonic, and the energy levels are unequal. And in particular case, I will prove later on that the separation between the conjective energy is actually decreasing. And therefore, we can say Josephson junction as a non-linear element. So in this case, the potential is not quadratic. It will going to have a term of 4, 6, and 8, and so on. And also, we called JJ as a non-linear element. And because of this non-linear element, this non-linearity contribute to a non-linear inductance. And what is that? Lj, which is equal to Lj naught upon cos phi. So you can see that our inductance is actually a non-linear. So this is the way you can see that we can make the harmonic oscillator into a n-harmonic oscillator. I think I tried my best to finish it, but it is not possible to do it today. Then I think up till here is done. This is a basic mechanism in all types of superconducting qubits. Whether you talk about a charged qubit, you talk about transmons qubits, you talk about a flux qubit or phase qubits or any qubits superconducting. This is the basic circuit diagram. Okay, so you're going to have one Josephson junction, and it is in parallel with the one coupling capacitance. And here something we will talk about tomorrow. So this is the basic structure for all types of superconducting qubits. And now then tomorrow, what we can do, we can discuss the first one, that is called the charge qubit, also called Cooper pair box. And then of course tomorrow I will discuss the other types also, transmons also, and phase also, flux also. Okay, all these three category we will try to discuss, but more mathematics is involved. And without see, if I simply tell you that what is the charge qubit, because it is very important to understand, okay, that these charge qubits, they behave very much similar like a spin qubit. But in the spin qubit, you had a very good clarity that in the blosphere, these qubits have some direction, and then you can rotate them. And I'm going to tell you that here also, in the case of a charge qubit, I am going to represent, okay, this charge qubit in the blosphere. In fact, on the day one, you asked this question that can we represent, okay, can we represent a blosphere for a different system? I said yes, but with a change in the mathematics. And that is the change in the mathematics we're going to do tomorrow. I will show you that this uh, charge qubit or transmons qubits, whatever you think about, they all going to actually perform similar like a spin qubit. But of course, they're not a spin, but we can represent them on the on this uh, blosphere, where here we call this is the 0 state and this is the 1 state. This is nothing but a spin down. This is nothing but sorry, spin up, and this is nothing but a spin down. Very easy to understand. But here I will tell you that here also I will call 0, but this is going to call as the N0, and N0 is called no excess of 0 excess of extra Cooper pair. And here I will call 1. So means this is actually equal to 1. This means 1 excess Cooper pair. And similarly, I will show here that this state, for example, in the case of your spin qubit, I call this as the plus, this as the minus. Here also, I'm going to call a plus, and you know that this plus 1/2√2 and 0 plus 1. So here also I will say that the same thing. It is a superposition of the no Cooper pair and 1 Cooper pair. You understanding? So
Sir, two things to say.
mhm.
One is the first one is actually it is happening in a very short time. So some note, if you give some notes about that, it will be helpful, I think.
Yes, I will actually. Yesterday I was somewhere involved, so I could not send, but I will send both the notes yesterday and today to you.
Okay, that will be helpful
Yes,
actually.
yes.
And today there was a schedule of quiz through which we may self-assess ourselves.
This will be take place tomorrow. No?
Okay. Okay.
Yes. Anybody else want to ask any question?
Yeah, hello, Sugam.
Yes, Jovin.
Yeah, this is regarding the difference between the LC and the Josephson junction and the capacitance circuit.
Yes.
So
Mhm.
when we draw the potential diagram, in the first case, the flux equal to 0 is a stable equilibrium, but in the other case, it's an unstable equilibrium. If you look at the potential figure,
Mhm.
because second one is a cosine phi graph,
Mhm.
right?
Yes, yes.
So phi equal to 0 is an unstable equilibrium in the second case.
Yeah.
So does it create any problem or difference?
Just it is taken care very carefully. This is the thing I will discuss tomorrow. Okay.
Uh-huh.
Very important point, but I will solve through some mathematics. Okay.
Okay.
So I will draw two potentials well, and then I will
Mhm.
show you how this phi 0 playing a role here. But just
Okay.
wait for one day, okay? Because this needs some mathematics.
Okay.
Yeah.
Right.
But good point.
So here also uh, since we have a quantumness, we are kind of extrapolating the spin mathematics we have done to this system, right?
Yes, exactly. I will when we will do this mathematics tomorrow, you will see a similarity completely. Okay, that the Hamiltonian, which I'm writing for the spin matrix, spin
Uh-huh.
qubits, a similar kind of Hamiltonian is also for the charge qubit. But the
Uh,
terms
yeah.
will be different. For example, here you will use magnetic field. There you're
Mhm.
going to use some energy. Okay. Which is
Yeah.
going to act like a magnetic field, okay, divided by H
Yeah.
cross, okay. But it will go into very nice correlation.
Yeah.
It would have
But
been good if I have finished today, but I
sure.
think
Yeah.
it's mathematics, but I think doesn't matter.
Yeah.
We will try to cover to
Yeah,
tomorrow.
it's nice to see the connection, but then in a spin qubit, we have the flipping, right?
We have a
But
flipping exactly.
yeah, but
And
but
here,
here
here we
is it
will
like
have, here
huh,
it will be like, no, you can think like there is a platform and
huh.
I'm pushing one Cooper pair here, okay. And then
Yeah.
taking back, again pushing
It,
here, taking back.
so
So,
it's like
so
creation, annihilation,
creation
then
and alienation,
inhibition.
exactly. Yes, that's
Yeah.
true. So I'm creating one Cooper pair and then taking back. And
So okay.
if both are in superposition, then you can get the superposition state.
Yeah. So then it is also position dependent because superposition is it like it's halfway or something? Is it that sort of a interpretation?
See, it's the
I
quantum
don't
mechanics.
know.
I mean,
Yeah.
we should not use the word position now because it's a
Yeah,
quantum
right.
it's a quantum mechanical system. Okay, you cannot
Yeah.
say that okay, this is moving and is now at this position or this position. We
Right.
can simply say okay, yes or no. So qubit is there or not there. Okay.
Right.
I mean, it's not possible to say for anybody that okay, now qubit is somewhere here, now here, now here. Okay.
Uh-huh.
Is the
Okay.
probability will be there or not there?
Right. Yeah, nice. Thank you. Yeah.
But it will be a nice correlation you will see. Maybe only understanding one type of qubit, like a charge qubit, you will get the full clarity. And even if I don't discuss the, let us say, photonic qubits,
Mm-hmm.
so everybody will have a very good idea that, okay, doesn't matter. No? We don't need always spin a vector. Okay, you can create this qubit and put on the this blocksphere, just taking some different analogy or different energy terms.
Right. Yeah.
But
Yeah.
this is something I think we will be able to conclude much better way tomorrow when I will
Okay.
going to summarize.
Sure. Yeah.
Okay, anybody else? Okay, I think Shankar not here. Na? I think he
Yeah,
already left.
I'm back actually.
You
I
are back.
joined after some time. Yeah, Shankar had to leave. Yeah, okay. So today's session we are concluding now.
Yep.
Okay. So then see you tomorrow.
Okay, see you everybody tomorrow.
Okay. I will stop recording.
Thank you, sir.